Good morning, dear participants. Today is the fourth day of our FDP, Geomechanics for Structural Engineers, and the first session will be handled by Dr. R. Shivashankaran. Sir is a senior professor at NIT Surathkal. He did his BE Civil Engineering from University Visvesvaraya College of Engineering, Bangalore, MTech from IIT Madras, Doctor of Engineering from Asian Institute of Technology, Bangkok, Thailand. Since 1995, he's been a teaching faculty at NIT Surathkal. He's held offices of Dean, Research and Development, Editor-in-Chief of NITK Research Bulletin, Chairman, Research Advisory Board, NITK Surathkal, and many other posts. He has more than 42 publications, has guided more than 15 PhD students, a man with vast academic experience. So it's my pleasure and honor to invite Dr. R. Shivashankar to handle the first session of day 4. Thank you and welcome, sir.
Thank you for those introductory remarks. Can you hear me?
Yes, sir. You're
Okay.
audible.
Okay. I'll start with presenting my slide. Can you see my slide?
Yes, sir.
Okay, thank you. First of all, I would like to thank the organizers for giving me this invite. Although uh, I'm more of an academician than a designer and more into geotechnical, but we have been working on soil structure interaction. So I'll share whatever that I know. So, my title was Geotechnical and Structural Design of Foundations. Just a brief look into the current practices and also a look into soil structure interaction. As I said, we have done some studies. Some of our PhD students worked on SSI, and also I love to talk about geopractices. In civil engineering, if you are looking from the point of view of building, a multi-storied building, or any building for that, or any structure for that matter, there are two components. One that you see above the ground, which you call superstructure, and the other part, which is below, which is called the substructure. So the superstructure is seen above the ground, appreciated, and it looks beautiful. The substructure includes the basements and foundations, so it's all buried, not seen. All these three form an integral part, so they are same. That means they are dependent on each other. It's not like the superstructure is different from a substructure. The substructure gives stability, and the nature of superstructure also decides the behavior of substructure. So we will try to see some of those things. I just took out this photograph during one of my visits abroad. You'll see that there are a lot of structures above the ground. So infrastructure is important for economic development, and that's also what we are emphasizing in our country. As I said, they are above the ground, seen and appreciated, but there is something below the ground also, substructure. As much as above the ground, the substructure is typically same depth into the ground. right? Approximately, though not exactly. As I said, these are buried structures and not appreciated. They're the same integral part, but you can say they are sort of interdependent and they interact with each other. Okay, sorry. Now, if you go to the design, at least in India, the superstructure cost would be about 80 to 85% of the total cost of the project. I'm talking from the point of view of multi-storied buildings. Substructure will be about 10 to 15% typically. But in many situations where there are problematic soils, sometimes the cost of the substructure, the foundation will be much higher. You may have to use piles. Whenever you use piles, the cost of the structure increases. The substructure cost could exceed more than 50%. But in most of the places in India, the soil is good. If you have such a proportion of more than 50% substructure, you will be branded as a poor engineer, and you may not get any more projects. Also, the one important thing that I noticed abroad and which is somewhat lacking in our country is that in every major project, you should have a thorough geotechnical investigation. Uh, about 1 to 3% is spent on geotechnical investigations, but that's very rare in India unless it's a very important and major project. And also, a lot of instrumentation are put beneath the structure. In the structure, you may have settlement gauges, pore pressure transducers, you may have accelerometers for monitoring earthquake motion. But somehow it's still lacking in our country. That instrumentation is very rarely uh, seen, because if you have instrumentation, uh, you can measure the settlements, you can measure the deflections, you can measure the pore pressures. So, and you can actual measurements of the structure, and you can compare this with your design. In your design, you would have predicted some settlements, predicted some base pressures. So you can compare your design with the actual uh, data obtained. So that helps us or gives us more confidence in our design. Sometimes what we predict is far away from the reality. That means either we would have over predicted or under predicted, and that's a problem. So we will never learn. So it's always important to have some instrumentation uh, from the practical point of view and also for improving our knowledge. One such thing is the soil structure interaction. So designers most often do the design of superstructure separately, assuming a fixed base, and then the substructure, the foundation design is done without considering the superstructure. So that is sometimes not the real case, not the reality, and then we end up with wrong predictions or over design many times. So in engineering, economy is also very important. So if you use a, a proper design, we can achieve good economy. I just would like to quickly run through some of the civil engineering wonders I usually show in all my lectures. This is because these structures are wonderful to see. You have Petronas Tower, the Golden Gate Bridge, and our own Howrah Bridge, the new Howrah Bridge. This is a bridge over River Potomac in Washington. Why I put this is I like the architecture of this. It's beautiful to see, because civil engineering is not just about providing the facility, it's also about aesthetics. And it's another view of that Potomac Bridge. We have dams, we have transportation, high speed rail, and over bridges, and we have telecommunication towers. Sometimes we also have to deal with very difficult terrain. Uh, and so we cannot say no to any situation, whatever the tough situation, the field situation. I mean, we have to design, provide a design. And so these are normal structures. These have usual dead loads, live loads, and lateral loads. Lateral loads could be either wind load or earthquake load. We take the worst of the wind load and the earthquake load, not both of them together. But sometimes the clients and the architects want some very unusual structures, which are good to see, but not normal structures. So the loads will be very different. There will be large eccentric loads, large inclined loads, large moments. In such cases, the foundation also becomes a very important. It has also to be designed specially, and the cost of the substructure also will increase enormously. So we have some structures which is overhanging on all four sides, or you can have a very thin structure. uh, must be one of those cell phone companies, and here the aspect ratio is so high that there will be enormous wind load, and you got to provide some suitable pile foundation, or some building like this, or this is the Vienna University in Austria, or you must have seen this building in Republic of China. So all these are structures that are built, but supporting them is also the foundation. So the foundation also will be complex, and you'll have to understand the relationship between the foundation and the superstructure. I'll just briefly brush up some aspects of geotechnical engineering, particularly the foundation engineering. Uh, so, geotechnical engineering deals with soil, rock, and groundwater. So, it's almost every structure on Earth, above Earth, below Earth are supported on soil or rock, and so the load is transferred to soil or rock, and so it has applications in every discipline: military, mining, petroleum, and also in in our own other civil engineering branches like environmental engineering and structural engineering. So mainly as a geotechnical engineer or a foundation engineer, we deal with the interface between soil and rock, with or without groundwater. All soils are good in the dry condition. All soils are good when they are properly compacted. But they become problematic when they come in contact with water. We love water, but just the sufficient amount of water, which we call the optimum moisture content, to facilitate compaction. At OMC, the soil is not fully saturated, just about 80-90% perhaps. So, soil behavior is very difficult to predict, especially when it has water. Uh, we had the classical Terzaghi soil mechanics that most of us have studied, but nowadays a new approach called the unsaturated soil mechanics is coming up, and I think that will be the future, because in unsaturated soil mechanics, soil has solids and voids with water and air, and there is the air has could have some suction, so tension. So all those things are the new approach in soil mechanics. So whenever I say geotechnical engineer, coming to the practical aspect, we deal with bearing capacity. We say ultimate bearing capacity, safe bearing capacity, allowable bearing capacity, and we don't want the stresses beneath the footing to exceed SBC. And in case of shallow foundations, there should not be any negative or uplift pressures. So if there are uplift pressures, if there are large lateral loads, we have to go for pile foundations and settlements. And also, so we want the load to be safely transferred. The contact pressure should not exceed SBC, and then there should be no tension. And also the settlements. When I talk of settlements, both total and differential should be within permissible limits. preferable not to have any differential settlement. And we should make the ground resistant to earthquakes, because there are two situations. When the structure may be on hard soil, there's a different type of failure, and when the structure is on soil, silt or clay or fine sand, we will have the problem of liquefaction. So I don't want my structure to get I don't want my ground to get liquefied, which means there will be a temporary loss of bearing capacity. If time permits, I just touch upon some aspects of slope stability. And as I said, two very important things in practical geotechnical engineering is you should do proper compaction, and you should follow proper drainage control. You should control the water, right? Then coming to slope stability, sorry, I'll make it full screen. Okay, coming to slope stability, what we have studied from geotechnical engineering is only that the slope step, we have the resisting and the driving forces, and we say there is cohesion and friction. It's not just that, there are also hydrological factors, and it's also, slope stability is also about bioengineering, biotechnical engineering, because there are a lot of vegetation. You may have grass, you may have big trees. What's the role of them? Sometimes they improve the slope stability, sometimes they cause instability. So as I said, for poor grounds, we come across poor grounds, and the same soil or the same ground can have different bearing capacities. With water, it will be very poor, and we don't want the soil to be, so we want it to be less compressible and good earthquake resistance. Soil is said to be a micromaretic fluid. That means soil, as you know, is a three-phase system, and saturated soil is a two-phase system. And micromaretic fluid means sometimes it behaves like a fluid and sometimes like a solid. So we should know both fluid mechanics and solid mechanics to understand soil mechanics. So as I said, nowadays the trend is towards unsaturated soil mechanics, and a lot of research and the design, the understanding is towards this unsaturated soil mechanics. So this you must have seen in the textbook by Holtz and Kovacs. That is some clays, I mean undisturbed marine clay, which is taken from the bottom of the seabed. When it's undisturbed, it can take some load, quite some load, more than 10 kgs. But the same soil, when it's put in a beaker and stirred and you pour it, it flows like a liquid. So that means liquids don't have any shearing resistance, any shearing strength. So the shear strength is lost on disturbance. So we call such soils as sensitive soils, usually clays, sensitive clays. So that's the practical significance of that is if let us say I have a structure already existing on pile foundation and my adjacent site is vacant, and the adjacent site owner decides to build a multi-story building, and he adopts driven piles that are precast and driven. So if the soil is sensitive and if it's driving, those vibrations can disturb the piles under my structure, right? That means the strength of the undisturbed soil could be as low as 1%, right? Or it can be it can lose 50% of the strength. So depending on the sensitivity, some clays are very sensitive, highly sensitive. So there will be a loss of strength even in shallow foundations as well as deep foundations. All these are really very difficult to implement or incorporate in a real soil structure interaction study. Perhaps there is a lot of scope in future to deal with that. So as I said, geotechnical engineering, well, in my student days, it was said that biology has no importance. But nowadays, biology is one of the very important subjects for civil engineers, especially environmental engineers. Now, so nowadays we have environmental engineering or environmental geotechnics. We deal with the pollution of soil, water, air, and also transportation. So there is transportation geotechnics and structural design. So structural engineering, because whenever you design a structure, you also have to look into what is the type of soil. That's very important. Whether the soil is sensitive, whether it's reliable to liquefaction, or if it is weak, highly compressible, and low bearing capacity, then you have to adopt some sort of ground improvement technique. So it's not that a structure can be designed. A civil engineer can don the hat of both structural engineer and geotechnical. I'm not making any difference between structural and geotechnical engineer. The civil engineer has to understand that he also has to consider the type of soil and what is the impact of the structure the on the on the soil and its especially in seismic zones. And another important branch of geotechnical engineering is forensic geotechnical engineering. So we have a lot of failures around us, slope failures, building failures, so many failures. We have to analyze and see what are the reasons for that, what was not done properly. So it's not just failures that constitute forensic. Also, some structures which should have performed extremely well, we have to study that also. That also constitutes forensic geotechnical engineering. And nowadays we have a very very much sort of the subject of marine geotechnology, wherein you have to deal with some offshore structures. Well, I just so as I said, if the ground is weak, we'll have to improve it. So that's one of the uh, important things. And in foundations, we have the shallow foundations and deep foundations. So it's not like you can support any structure on pile foundations, but you should not always choose the pile foundation. It should be the last option, like just like it's called the just like the doctor diagnoses a patient. The doctor first treats him with some mild medicines and maybe some stronger medicines, then injections, and the last option is surgery. So like that, the last option for foundations should be pile foundations. Nowadays, deep foundations are almost synonymous with pile foundations. Now, in the design, the geotechnical design is governed by limit state of serviceability. That means we are restricting the settlements because there could be so many service lines below the building. There could be sewer pipes, there could be water supply pipe, gas pipe, and so many cables. And we don't want all of them to get damaged. So our building codes restrict the settlements. But the soil or the ground is capable of taking much higher load if you allow larger settlements. For example, our agricultural engineers, they don't have any limitation on such settlements. So if you ask an agricultural engineer what is the load carrying capacity of a soil, he may say 1,000 kilonewton per meter square. But a civil engineer says it's only 150, same soil, because we are bound or restricted by the settlements. Our settlement should not cross a certain prescribed value. Okay, and so we know that foundation is a media for transferring loads from superstructure to the substructure, and as I said, we need to worry about the groundwater, and there are two types of foundations, shallow and deep. The highest denomination in shallow foundations is the raft foundation. and the load is transferred by bearing. That means we make an excavation and then lay the foundation, so we are able to see the soil to which the load is transferred. But in piles, there are again two types: bored piles and driven piles. Usually, we get an idea of the type of soil in the case of bored piles, because in bored piles we remove the soil and replace it with concrete, so they are called replacement piles. So uh, but not the proper nature of the soil in its natural uh, environment. But in case of driven piles, we are driving the piles and forcing the soil to displace, make way for the piles. So again, piles are of you can say they are from 7 centimeter to 7 meter dia, and they can be end bearing piles and friction piles. So we use piles when the loads are very large. When I say loads, I mean all the vertical loads, compression and uplift loads, lateral loads, which are wind and earthquake. So, and also whenever the soils are problematic, as I told you, we have a lot of sensitive soils, loose soils, and also expansive soils. You must have heard of black cotton soils. So, in all such situations, we use piles, and also whenever erosion or covering is likely to occur, like in the case of bridge structures, bridge piers around below the bridge piers. So, or whenever there is a deep excavation expected in the adjacent site, we go for pile foundations. As I said, pile is the last option because when you use piles, your cost of the structure, overall cost will increase, and the substructure cost will also increase. And okay, sometimes uh, the soil in its natural state has a certain SBC, and if I put piles, the SBC will be it will be increased enormously, maybe 20, 30 times. I don't need that high bearing capacity. Maybe I just need to increase my bearing capacity 2 to 3 times. In such situations, there are many ground improvement techniques nowadays. So between the shallow foundation and the pile foundation, for just about little increase, we can go in for ground improvement techniques. And again, coming to design of foundations, whether it is a shallow foundation or a pile foundation, we have two types of designs. One is the geotechnical design, and the other is the structural design. It also means that there are two capacities: geotechnical capacity and structural capacity. When I say geotechnical design, I design the depth of foundation, the size of foundation, type can be isolated or combined or raft, like that. And in case of piles, the diameter of piles, length of piles, the arrangement of piles, spacing, group of piles. So if if a design problem is given to a group, let's say a group of 10, 15 people, each will come up with a different design, because there are so many options. You can have a large number of small diameter piles for a structure, or a small number of large diameter piles, or you can have a large number of short piles or a small number of long piles. Again, you can have driven piles or bored piles. Usually, the driven pile capacity is increased after installing piles, because you are forcing the pile into the ground. The soil around and beneath is compacted. But in the case of bored piles, you are making a hole in the ground, which means that you are releasing the overburden stress. You are also making a borehole, drilling a borehole, so there'll be a lot of soil cuttings which will accumulate at the bottom. It is very difficult to clean. Practically, if you ask a piling engineer, it's very difficult to clean the bottom of a borehole even with high air pressure or water pressure. So the IS code suggests that you can slightly increase whatever you have calculated theoretically. You can increase it by about 10-20% in case of driven piles, but in the case of board piles it says the end bearing has to be reduced by one third. That means whatever the end bearing for driven piles, supposing 100 tons per meter square, that same for the board piles is only one third, 33 ton per meter square. But uh, so all this again, if you use a group of piles, there is pile group uh, interaction. That is, we have group efficiency, we have interference of piles. So all this to be incorporated in the soil structure is really difficult. Uh, Finite element itself is an approximate method, and we make further approximations. As I said, our aim is to predict the load carrying capacity and the settlements as close to the reality as possible. So whenever our inputs uh, are more real, then only our output also will be real. And okay, now so I said that board piles, the bearing pressure, the bearing capacity is drastically reduced. And in the case of structural design, this comprises of geotechnical design, which means that I'm sorry, which means that if there is a load on the pile, I assume that that load is taken up by side friction or skin friction or shaft resistance and end bearing resistance, right? So total load QU is taken by shaft resistance and end bearing resistance. But the other part is, so if the, and that means that when I'm transfer, that means I'm transferring the load from the superstructure to the pile by skin friction and end bearing. And in the process, in this process, there will be some settlements. The skin friction will be mobilized only when there is settlement. I don't want the settlements to exceed the permissible limits, either in the case of single piles or group of piles. So that comprises the geotechnical design. Coming to structural design, so I know how the soil bears the load, but the load is transferred to the structure, to the body of the pile. So when I'm applying a load on the pile, it should not get crushed and fail by compression, crushing. So my pile should be structurally sound. That means it should be made of strong concrete with sufficient steel. Usually a group of piles are covered with a pile cap, and uh, and usually in design, what we are taught in textbooks is to make the footing or the pile cap safe in shear without any shear reinforcement. But many designers also use shear reinforcement. You know, shear reinforcement in beams are in the form of stirrups. In slabs or in slabs like footings and pile caps, you can have vertical reinforcement between the top layer of reinforcement and the bottom layer of reinforcement. Okay, this is just a figure I liked from the internet, and it shows how a pile was completely exposed. So it shows that it's not like that. If what we do in the design is, in the design offices we have a structural division and then a geotechnical division. The structural engineer, I'm again telling you, I'm not making any difference, but the person doing the structural design, he designs the structure, whatever the number of stories, by assuming a fixed base, right? He's not worried about the type of foundation and the type of soil. So he does the structural analysis and then transfers the load in the lowermost columns, the loads and moments, structural loads and all that. And the geotechnical group, the geotechnical engineer takes these loads, final loads provided to him from the structural section, and he designs the foundation. He's not worried about the what type of structure it is, what type of beams and columns are there, what type of slabs are there, and he just designs it. So this is wrong actually, and this is a gross what to say, you end up with very conservative designs, because even if one of the piles or one of the foundations in a big structure were to fail, it doesn't mean that the whole structure has failed. There will be a redistribution of loads, right? And then we always usually have enough factor safety, so the structure can still survive and continue to perform. So as I said, piles are piles. So what I mean to say is, whenever you deal with large structures, they're like say more than 5 stories, shallow foundations will not work. So it will be pile foundations, and piles are placed in groups. So we have the pile group efficiency or pile group interference. So we have optimal spacing of 2.5 to 3D. If I increase the spacing, the pile group efficiency can increase. Even if I get 80 to 85% efficiency, that is very good. But if I increase the spacing to 4D or 6D, then the interference, there'll be no interference, group efficiency will be 100%, but you will end up with a very massive pile cap. That means the pile cap becomes very unwieldy. So as I said, you should achieve economy, so you should have a compromise between efficiency and the pile cap design. So this is just from figures. So group behavior is different from a single behavior, and the group capacity is generally not equal to the number of piles into the load carrying capacity of individual piles. So as I said, if I keep my spacing large, group efficiency will be more, but the pile cap will become unwieldy. So this is how a stress bulb around a pile looks, and this is how the overlapping zones of the sorry, my figures aren't good. So this is the overlapping zone in plan. So that causes, so this will take one time QU is the individual pile capacity. Here there are 2 piles. Let us say the group capacity is not 2 times QU, that is QU is the individual capacity. Because of this interference, it may be 1.8 or 1.7 times QU. But if I increase the spacing, yes, these 2 stress bulbs will be independent. There will be 100% efficiency, but my pile cap becomes very unwieldy. It's like a beam. So if the span increases, the depth of the beam increases. Okay, that's what I said. So we have to make a compromise between efficiency and the thickness. Another important thing is, in geotechnical designs, you shouldn't take for granted the soil. You should have a thorough investigation done to find out the different strata, the depth of water table, how the water table fluctuates during monsoons and in dry season. Because whenever the soil is submerged, its bearing capacity is reduced by half. Right. So a thorough geotechnical investigation is very important. You have to also do a reconnaissance and observe neighboring buildings if there are any, and inquire on what type of foundation they are supported. So because economy and good performance are vital. So in the case of piles, you'll have to do a deep exploration, and you may also do some field load testing, like like a plate load test or a pile load test, and ascertain. But plate load test will give you information only about shallow, just about 1 to 2 meter of that. So you can go in for tests like the SPT or SCPT to give more data. This is one of the sites where some explore, because usually when we do soil exploration, we do it at some points, and we can't scan the entire area. So in one of the sites, the foundation was already being constructed. And at this point, when a foundation was also laid and the worker was hitting the ground with a pickaxe, then he heard a hollow sound and the engineer got suspicious and he ordered the whole area to be excavated, and it was found that there was a big cavity. So you have to be very watchful. So uh, this will be very unexpected and could lead to disasters. Now, I would like to I would like to explain a case study. There were two buildings. The first building was already built. This is in our coastal area where there is a lot of laterite. So the owners decided to build a second building adjacent to that, identical, exactly identical. They thought it's all same number of floors. So they said, why go for any geotech investigation? So we will just copy the same designs, right? So they had so this building was already built. It was built some years back and it was performing. And the second building was a new building that was just built with, it had just the columns and the beams and the slabs, the skeleton. But after a few days, this building started to tilt. And when they tried to investigate, they found that this original first building was resting on hard soil, whereas the second building was resting on filled up ground. This filling up was done many years ago, many decades ago, right? So you can't know. So this was not properly compacted, and then when this but they assumed that the second building is resting on similar soil and similar building, identical building. So this building started to tilt, and they had to do a lot of post-mortem work. They had to go to the basement floor, drill holes, and then drive some piles, small diameter piles, which are called micro piles, and also jack up. So ultimately, after a lot of effort, they could rectify the tilt, and now it's performing. But it involved a lot of cost. So if they had invested a little money, that's what I said. You can't take it for granted that just the descent site will be same. Even 5 meters, 10 meters away, the soil could be entirely different. So every case study, every project has to have a separate uh, uh, soil exploration. Now, as I said, foundation. I'm mostly dealing with foundations because that's what is appropriate for soil structure interaction studies. So we have the shallow foundations and deep foundations. Deep are generally the pile foundations. As I said, pile foundations are there from 7 centimeter to 7 meter, and their lengths vary from about few meters, 5 to 6 meters, to more than 100 meters. Offshore piles are much longer. And so, as I said, whenever you have a project at hand and you have to decide the foundation, you should start from the lowest denomination. Piling should be the last one, because, of course, with all apologies, if you go to a piling contractor, he will always recommend a pile foundation, but it's not you have to see the pros and cons of using piles. Again, there are two types of piling contractors: board pile contractors and driven pile. So if you go to a board pile contractor, he will say go for board piles. Driven pile contractor will say go for driven piles. You should know that driven piles are to be cast in the casting yard. They have to be transported and then driven, installed. So there are limitations in size. You cannot have very large diameter and large size piles. Usually half a meter dia and about 20-meter long is the limit for driven piles. Any other pile, 7 meter, 100 meter, it always has to be board piles. But the problem with the board piles is that you're disturbing the soil, the bearing pressure is reduced. And we're making a hole and putting concrete. We don't know where the concrete goes. What happens to the concrete? So supervision at site is very important. And in case of board piles, it's generally required to socket the piles into the hard intact rock. So these are some of the independent isolated footings. We can have a footing of uniform thickness. We can have a footing like this step, or we can have a tapered footing. So geotechnical design requires us that the base pressures all should be compressive. Contact pressure should all be compressive. Settlement should be less than permissible limits. And so that's the, and also the depth of foundation. That's geotechnical design. Coming to structural design, we designed this footing slab as a footing as a slab, right? So we'll have to check for shear. We usually check for one-way shear and two-way shear and punching shear. We check for bond. So we check for flexure, how much. So the IS code recommends, so I'll not be going in detail, says that the critical section for flexure, for bending moment, is at the face of the column. So for that bending moment, you should have enough steel, right? And also there are IS 456 recommendations on what should be the minimum steel bond length and all that. So all that, and also many other clauses are there. So all those have to be satisfied as per IS 456 for RCC design. So that comprises the structural design. So a footing is not just a geotechnical design. One aspect is geotechnical. That is, I assume the load to be taken by bearing and settlements is the concern of foundation engineer. And the other things, the reinforcement and the grade of concrete, thickness, etc., all come under the purview of structural engineer. So, so a footing is a combination of geotechnical and structural designs. So if the two independent footings are very close, we join them with the combined footing, maybe 2, 3, 4 you can combine, rectangular or trapezoidal. If there are more independent footings which are very close, we all combine them with a slab, or we may have some ribbed raft like this with the main beams and cross beams. So this is the highest denomination in shallow foundations. That means the load is transferred through end bearing. But if the soil at shallow depth is not capable of withstanding the loads from the superstructure or safely transferring the load from superstructure to subsoil, we go for pile foundations. So this all I have said, I think, in my different. So again, the code also says that the load should be safely transferred. In case of shallow foundations, there should not be any tension, and settlements should be within permissible limits. These two are very, very important, and also the ground should not liquefy, right? And whenever it says that there should be minimum eccentricities and all that, but that's not in the hand of the designer. If the client or the owner wants a very unusual structure, we saw so many unusual structures, yes, we should be ready to design that. We cannot say we cannot design, we have to design, but you have to impress on the client or the owner that the cost of substructure will increase enormously. The foundation cost could be more than superstructure cost. So as I said, all textbooks teach us that the foundation has to be designed as a slab without shear reinforcement. But you can also have shear reinforcement. That means you can have a top layer of reinforcement, and between these two layers you can have vertical, just 2 bars. You can bind it to the top grid and bottom grid. Those shear reinforcements are also, that means the shear forces, the shear stresses are not just taken only by concrete. Here, of course, there is some shear stress taken by the main reinforcement, but you can also have shear reinforcement. Here again, when I say geotechnical design, there is not much confusion, because we take the load from the superstructure. I add 10% of the load from the superstructure as the weight of the footing. So my total weight transferred to the soil is this column load plus 10%. This I divide it by SBC. How you calculate the SBC is again a different matter. So I get the area footing. So when you put that area footing, that two things are automatically taken care of. That is, the contact pressures will not increase, and also the settlements would be within permissible limits. But for structural design, I can have a footing slab of very thin, maybe very minimum 30 centimeters, or I can have 1 meter also. When I have 30 centimeters, I have to provide more reinforcement. But if I have minimum reinforcement, I can have a thicker slab. So there's so many options. You can vary the thickness like this. So there is unique design. These are designs done in the conventional way. That's what is being followed mostly, and that's not the correct way. The structural analysis provides this load P and any other moment. So I just designed this footing, assuming this footing is the only one that is there. But this footing is not independent. It has so many other footings. Even if one footing fails, there will be a readjustment of loads, redistribution of loads. So that's why a soil structure interaction is very appropriate. And so uh, so the foundation should be resistant to earthquake. So you can use some ground improvement technique. And in case of machine foundations, there should not be any resonance. So you should play with the natural frequency and the operating frequency. Minimum eccentricities is generally not in our hand. If the client says, yes, I want it very unusual, uh, uh, very different structure, then we have to design it. And as I said, foundation design, the geotechnical design is a limit state of serviceability. I'm not utilizing the full strength of soil. I'm limiting the deflections. I'm limiting the settlements. So different type of structures have different permissible settlements. I may have a structure where I will allow 75 millimeter settlement. In another case, I may allow only 25 millimeter. And after all this, the foundation must not fail uh, in compression or whatever it is. So we have two capacities: geotechnical capacity and structural capacity. So if you take piles, the actual capacity of a pile is the lower of the geotechnical capacity or structural capacity. So it should not fail either in geotechnically. That means if the load is very high and the soil around is very weak, it may settle. It may settle large amount. So large settlements are deemed as geotechnical failures. And other one is that the pile itself may get crushed. Pile is designed as a compression member, as a column. So I don't want it to get crushed. And you'll also long columns. You'll also have to consider the effect of buckling in some cases. So finally, I want my foundation not to settle too much. Load should be transferred safely, and it should not get crushed structurally. So this is what I've been telling. I think so. We use the limit states of serviceability. The area footing is the total load divided by SBC. So here I consider 10% as a self weight of the footing, and different structures have different permissible loads to ensure the safety of service lines, right? Gas pipes, water supply, sewerage, all those things. So these are the different clauses in IS 456, which tells about the critical sections for flexure, for one-way shear, and punching shear, or punching shear is also called two-way shear. Now, in spite of all these, uh, of doing a good design, good construction, there'll be failures because sometimes the designs are wrong, the assumptions are wrong. Usually, the conventional method, that is not adopting soil structure, we over design. We are supposed to have over design, but still there'll be failures because maybe the quality of construction is poor or the quality of materials is poor. Sometimes we might have constructed it very well, we might have designed it very well, but still there'll be some failures because of some wrong decisions, wrong judgments. So I would say poor construction practices. So, so we'll see some of these in later slides if time permits. And there is nothing. Some design offices, I'm told, they have a standard design made, ready-made. They have a template for every. If I say 50-ton load, they have a design. 80-ton load, they have a design. But somehow I'm not convinced with that. There cannot be a one design suits all because the type of structure, the type of soil, everything could be different. So you have to treat each case as as a separate and do a thorough geotechnical investigation. So you should not allow failures because post to do any rectification, post-mortem work will be very expensive. And as I said, forensic engineering is not just about failures; it also includes structures that perform well. Well, I think this is again a repeat the critical sections for design of footings, and we know that from civil engineering, any design we do structural design, there are two important things. We have to draw the shear force diagram and bending moment diagrams, and we have to provide steel wherever there is tension. For example, if you take a simply supported beam, the tension zone is at the bottom and you got provide steel at the bottom between the supports. But in the case of cantilever, the tension is at top. Likewise, in footings also, footings are no exception. They're also same. You have to provide steel in the proper tension zone. And you have to take care of compression, uplift, shear, all that. In structural designs, our loads are factored and we try to use the maximum strength. The loads are factored and we design for flexure. That's what we saw, the different sections, shear, and all that. So SBC, you can do an open pit sampling, or you can do a plate load test, or you can do a SPT, standard penetration test, SCPT, static cone penetration test. We consider different loads, and normally for tall structures, the lateral loads are more critical, that is wind loads and earthquake forces. We consider either the worst wind load or the worst earthquake. We don't consider both of them to occur at the same time. So we know from the structural engineering parlance, if my ground is very hard and there are no settlements, very good, right? This is the ideal situation. But if there is compressible soil, same nature of soil throughout beneath the structure, and the whole building settles, that's called total settlement. That's also fine. There'll be no structural distress, no structural damage. So today's ground floor may become tomorrow's basement floor. But if each column is if each column is supported on, if one column is supported on hard strata, one line of columns, another line of columns on soft strata, then you have differential settlements. And you know, if we must have studied in structural engineering sinking supports, so that will have additional moment 6EI delta by L square, if I remember correctly. So we might not have considered that additional moments, and that might cause the structural members to break and cause failure. So settlements are important to be tackled in civil engineering from a geotechnical engineering point of view. And there are, and also during earthquakes, the ground should not get liquefied. This is a structure. Um this is one of the famous earthquakes, the Niigata earthquake of 1964, wherein the ground liquefied. When the ground liquefies, it loses bearing capacity temporarily, just for a few seconds. And during those few seconds, it has no bearing capacity because the water has come to the surface during the earthquake tremor. So the buildings tilt. In this case, uh, there is no liquefaction everywhere. Only some pockets got liquefied and buildings tilted, but not a single window glass pane was broken. So this one type of failure on soft ground, on liquefiable grounds. So, and this is the 1994 Kobe earthquake. It was earlier thought that clay soils won't liquefy, right? But subsequently, in Japan, it's mostly clay. So it was found that this bridge also uh, tilted because of liquefaction of the soil beneath the foundation. So then people started studying about liquefaction of clays. And this is a structure on very hard soil. So on hard soil, there is so much shaking that the whole building breaks up. All the structural elements are broken into pieces, right? So you can compare a soft ground and a hard strata. The types of failures are different. So here we have to improve the ground. Here you have to provide maybe some sort of extra steel for resisting the earthquake forces, or you must have some sort of a base isolation. So another example of a liquefied ground and a structural. So I would like to briefly touch upon some of my experiences with soil structure interaction. I owe it to all my PhD students because I learned a lot from them. And as I said, the traditional method is both the structural and geotechnical engineers work independently. The structural engineer assumes fixed base. He uses all wonderful softwares and gives some forces and moments. He assumes fixed base, is not worried about the type of foundation, the type of soil. And the geotechnical group will take that load and design a foundation as if the failure of one foundation will cause the failure of entire structure. I told you that's not the case. But this is not the correct method because there are so many columns, so many footings, and even if uh, one footing is not properly designed or constructed, hopefully, then there will be a readjustment of the load. There will not be a total collapse in most of the cases, right? So we should consider, the structural engineer should consider the type of soil and presence of other footings, and even the geotechnical engineer should consider the superstructure rigidity. That is, if the columns and beams are very heavy, very large size, the structure will be very rigid and there will be not much of differential settlements, right? So it also depends on the type of soil. Soil, as I said, is very complex. They are layered and it can vary horizontally also. This is one of the case studies in New Zealand, which failed, and failure is attributed to having not considered the soil structure uh, interaction, dynamic soil structure interaction under seismic load. So simply talking, if I assume a stiff soil and a structure, the bending moments and shear force diagrams will get. But when we assume a flexible soil, that means here we are. This is as good as considering the base to be fixed, and you can forget the soil, right? So stiff soil. But when the soil is flexible or sinking type, or it undergoes settlements, then the type of bending moment and shear force diagrams are different. I told you that in the structural design, we designed the structure for the maximum bending moment and shear forces. So considering the flexibility of soil will give you altogether a different bending moment and shear force diagrams. So I'd like to take two or three cases. One of the case study we studied was a chimney pile draft soil system, right? So there's a chimney, a tall chimney, 300, 400 meters, and this is a 30, 40 meter raft foundation resting on soil, and that's supported on piles. Piles are arranged in concentric circles. So I'll not go into the details. Uh, the ANSYS software was used, and I just want to tell my the people listening here, there are two types of pile groups. One is called a rigid pile draft system, in which there is a pile and a pile cap, and the pile cap rests on the ground, right? So the pile cap also acts like a raft. In the other one, in offshore piles, there are piles and the pile cap is well above the ground. That means well above the high water level. You have a free board. So these are called freestanding piles. So we should compare freestanding piles and rigid pile draft system. So this is a pile draft. That means my pile cap is resting on the ground, also acts like a raft, supposed to take some load. So so as I said, the conventional method is in the structural analysis to assume rigidity at the base, but in reality, the foundation is on flexible soil, and that will have a lot of that will make a lot of difference in the analysis. So the problem was we took up a chimney of two heights, 300 and 400 meters, and the various other parameters, slenderness ratio, that is ratio of height to base, was 12. Ratio of top diameter to base diameter was called taper ratio, was 0.6, and ratio of base diameter to bottom thickness. So these are the different parameters considered, and the same thing is tabulated here. It shows the diameter of the base, diameter of the top, thickness at the base, thickness at the top, and two heights were considered. So what we were interested, there's a particular IS code which is considering a fixed base, and we tried to compare. We did a soil structure interaction analysis and compared with the IS code, which is no interaction. So and these are the other geometric parameters. Outside diameter, this is the height, the two cases, 300 and 400 meter high, inside diameter, outside diameter to thickness, and all that. So thickness is the T is the thickness of the pile draft, the effective thickness, and the number of piles are as shown here. And three types of soils were considered, and the thickness of the soil below the raft was assumed as 30 meters, and below that is assumed the bedrock. And these are the different other input parameters: shear wave velocity, Poisson's ratio, and other things. And three types of soils were considered: loose sand, medium sand, and dense sand. So this is most flexible, and less flexible compared to fixed case. And the different types of elements that were used in the ANSYS for the chimney and draft and pile and soil are shown here. And this is the discretization, and also a seismic load was input, seismic load of El Centro, and these are the equations, and this is the conventional analysis as per the IS code. The big equations are the radius less than c is the radius to the center of the shaft, and I'll come to the results. The tip deflections we got with time are as follows for soft, medium, and dense soil, and for the fixed case. And This is the maximum lateral tip reflection. So as the so in the, if the soil is soft, then there are more lateral deflections. But if you don't, that is considering soil structure interaction for different flexibilities of soil. Don't consider soil structure interaction, you will see that the lateral deflections we get are much lesser, both in the case of 300-meter and 400-meter high uh, chimneys. And the base moment, this is a gross overestimation. Without soil structure interaction, you see it's almost 17 lakh something uh, and in kilonewton meter. But if I take soft soil, the moments at the base of the chimney are much less, both in the case. So we are over designing without the soil structure interaction. And so these are circular structures. So we consider radial and tangential moments. And the tangential moments for which we provide circumferential steel, the tangential moments got by the IS method, that is the conventional method without SSI, is much higher. But if you consider the flexibility of soil, the tangential moments are much less. So again, tangential moments by IS method will be overestimated. It's not always that way. If you see the radial moments, uh, the radial moments by the radial moments by SSI are much less. Right? Radial moments of SSI are much less. Considering SSI different soils, they are higher. Settlements also were calculated for very soft, for loose, medium, and dense sands. So, but you need a good software which will be which can analyze this, and you can catch the you can vary the parameters. You can do a parametric study, and you can find out. Sometimes our codes, sometimes they are over designing, and sometimes they are under designing. So it's always better to compare the codal provisions with some sort of soil structure interaction study. So the second study, we also did some. We also had a project under under with funding from BRNS, and then we did the experimental study at CPRI Bangalore. We used a traxial shaker. I just give the very basic study we did, and we had a shake on the shake table. We had the soil box, and in that sands of different densities were put, and we also used a geosynthetic as a base isolation, as a slip layer, and we found out, we tried to study the natural frequency of the system, soil foundation structure system. So this is the model, which is a 1/3 model of the actual size. And we used a geosynthetic HDP sheet. So we found that using a geomembrane or geosynthetic layer will reduce the fundamental frequency for fixed base in the XYZ direction. These were the frequencies. When you use dry sand, then dry sand with geomembrane further reduced it, but wet sand was still lesser, and geomembrane also had effect. So a geomembrane strip layer can be used beneath footings for base isolation. The other study we made was a tunnel of reinforced soil footing structure interaction. It's like this. We considered a building, and then we considered a tunneling done, just like for metro rail. So we considered a single tunnel beneath the multi-story building, the center lines exactly coincide. Then we considered a building beneath twin tunnels, and the building at some eccentricity from the center, at 5-meter eccentricity and 10-meter eccentricity. So we studied what will be the influence of the what will be the settlements. So greenfield, that means without the tunnel, this was the greenfield without the building, this was the settlement. But as the building is provided, the settlements were seen to reduce. That may be due to some arching action. So this is uh, a two-storied building at varying eccentricities, and four-storied building at varying eccentricities, and eight-storied building at varying eccentricities. So this is for uh, two, four, and eight-storied building at the center of twin tunnels. So you will see that the green field is more, but when you have the construction made uh, at the center, it has some sort of arching action, and then that reduces the settlements. So this also with the building and with the twin tunnels beneath and at 5-meter eccentricity, 10-meter eccentricity. So for the shake table test, so the natural frequency was reduced as the flexibility of the soil increased, and also the geomembrane had a very good effect on reducing the natural frequency, and also the vertical set displacements while tunneling was happening beneath is also important. So uh, I just like to quickly run through this. So we saw the buildings, right? And in our places, the ground is sloping, and the most common failures we see, geotechnical failures, are the slope failures. So slopes are filled up with vegetation, and there are many slope failures. So we have retaining walls. Slope failures happen because of wrong design and because of drainage, no control on drainage. Sorry. Some of the slopes are protected by some sort of retention structures like gabion walls, and many of the slopes are protected by grass, or what we call as turfing. And there is a particular type of grass which is called vetiver, which when grown on the slopes will provide a lot of stability. Uh, I'm propagating for this because this is a natural geosynthetic. That means its roots will grow up to 2 to 3 meters on the slope. When you go to any of the Southeast Asian countries and even Japan, the slopes are all turfed with vetiver grass. In our country, vetiver is also an Ayurvedic plant, right? In Canada, they call it lavanchana. So it's used for medicinal purposes. It's not a weed. The cattle will not feed on that. And it can sustain 2 to 3 seasons without rain, and it can sustain drought. So it's a very ideal material, and its roots are very strong. Its strength is almost 1/16 that of mild steel. So you can search the Google. There are hundreds of. You can search the vetiver website, www.vetiver.com. You get so much hundreds of case studies. So this is a well-grown vetiver root. So that means in every what I want to highlight here is in every system there is an interaction. Now the roots, if you take a tree or even a grass, let's take a tree. The tree is there. Its roots, let us assume, go deep into the ground, so they act like nails. They act like mechanical reinforcement. But the weight of the tree, the superstructure of the tree, will add to instability. It's a weight. If the weight is at the top or in the middle of the slope, it leads to instability. But the same thing at the toe of the embankment will add to stability. This root also acts like a mechanical uh, stabilization, and this weight also acts in resisting the failure. That's the one part of it. And also, whenever there is rain, the leaves of the tree will take the impact and reduce, so you will not have any gullying on the top of the slope. And also the roots will absorb the water. So when they absorb the water, they create suction. That's what I said in unsaturated soil mechanics. The suction is a very important thing. Whenever there is suction pressure inside, the shear strength of the soil is increased, right? And also the it reduces the flow, the impact of the flow. So that's a hydrological component. And also the tree root will take the water, and then there'll be transpiration and evaporation. So there's so many interconnected things, and all this will add to stability or instability. So in civil engineering, in slope engineering, we have to find out what are the resisting forces and what are the driving forces. It's like a boxing match, a boxing bout. So it's always that the resisting force should be more than driving force. So the ratio of that, we call it as the factor of safety. So the driving stresses and the shear strength. The shear strength could be cohesion, could be friction, and also the shear strength, the roots. I think so. One of the other most important thing is we should control the water. If the water is not controlled, sorry, I don't have it. If the water is not controlled, you will have scenes like this, because at the top the water was getting ponded and water was flowing through the face of the column, and also it's a steep cut. You can't have a steep cut. You'll have to design the slope, right? So, and of course, we can have different types of retaining walls: cantilever, counterfort, buttress. We can also have sheet pile walls. Sheet pile walls are piles, and they can be secant piles. Uh, Secant piles have a primary pile and secondary pile, and they can also be soldier piles with some lagging in between. Here in the secant piles, they are close to each other or they are overlapped, but in soldier piles, they are put at some spacing, and then there are some laggings in between. So sometimes I'll skip this. Sometimes sometimes you can also provide nailing. You can provide anchors, right? This could be an anchored sheet pile wall. So when you anchor it, then the sections and the depth of embedment can all be reduced. So there are so many softwares and also finite element you can use to find out the forces. As I said, the main thing, one is the geotechnical design, the lateral earth pressures, uh, the active pressure must be compensated by the passive pressure, and also you should make that member structurally sound. Sorry, sorry. Okay. So sheet piles are used for retaining structures. And also piles are not just used for foundations. They're also used in transportation infrastructure. You must have experienced, most of you, I'm sure, would have driven your cars and scooters. So whenever you approach a bridge, there is a slope, and there is a bump when you enter it and also a bump when you exit. That's because this bridge is on hard unyielding strata. This embankment is on soft soil. So what is done is the approach embankment is also supported on piles. Piles may be all of same length, and there could be some geogrid there, or the piles could be of reducing length as you move away from the abutment. So these are called as bridge approach support piles. So here the load is transferred by arching action. So that means the piles, there's a geogrid, and then you have the different pavement layers. So the arching action is considered. So here again the piles can be end bearing piles or floating piles, friction piles. And okay, another important aspect of soil structure interaction is, so we said we can have retaining walls, right? So if my structure is adjacent to a vertical cut, right, I'm in a very difficult situation. I have to construct my building adjacent to a vertical cut. So then what you can do is you can build this structure and then extend these beams at the different floors. You can have a column, so you can have a grid of beams and columns here very close to the cut or touching the cut, and there can be a slab between those beams and columns, a two-way slab. So these slabs, RCC slabs, are designed as two-way slabs, but for not for vertical loads like here, roof slabs, but for lateral loads. So you can have a soil, footing, superstructure, retaining wall interaction problem. What it means is that the weight of the building is utilized to resist the lateral forces. Otherwise, if you build a conventional retaining wall, it needs a vertical stem and also a base slab. Base slab means it will need a certain base width. You cannot, if the height of the wall is 10 meters, the base width has to be at least 50 to 60%. You may not have space. So what you can do is you can integrate the retaining wall with the structure. So the weight of the structure is made use of to resist the lateral forces. I think I'll skip this ground improvement part. So whenever the bearing capacity is low, you go for ground improvement. You do not want to increase the bearing capacity too much. You must have heard in the National Geographic channel and other channels that a Kansai International Airport is built on artificially man-made island, and it was sinking and it is still sinking a lot. So they have built intelligent structures. That means whenever the settlements exceed a certain limit, they get the message, and then they adjust the columns. There is some sort of adjustment the base of the column. You can increase the height of the column. So this also is a sort of a continuing soil structure interaction thing. And they have used a number of drains, what are called as vertical drains, prefabricated vertical drains. I think I'll leave it to, I'm running out of time. Also in soil reinforcement, you can also reinforce the soil. Maybe in some other occasion I'll try to talk about this, right? And also you can have reinforced foundations. So we can have, just like I told you in our lab, in our practical study with the shake table, we used a geosynthetic layer beneath the foundation. So we had developed some equations for that. And one important, one last thing I would like to say. I told you that this slide I'm repeating because you might have done a very good design and you might have constructed very well, but some of the judgment you make, some of the decisions you make may also be critical in design. So this is a very classical case of foundation failure in Shanghai. There was a multi-storied building, apartment building of about 23 stories. You can refer to this. Of course, you can Google it, you get plenty of data. So it is a 23-story building, and it's one of the many buildings. So this community decided to have a swimming pool. So they excavated 3 to 4 meters in one side, and all this excavated material they dumped it at the back. There was a river at the back, and one day it rained heavily. So when it rains, this is a surcharge load. Soil gets saturated, so its shear strength reduces because it's also helped by the river water. What you're doing is you're removing the resisting force in the front and you're increasing the driving force. That means the factor safety is being continuously reduced. So the engineer did not think of that. And usually we have a feeling that pile foundations will not fail. But one fine day, this building collapsed, right? Because it's not because of wrong design or poor construction, but because of poor judgment. So you have to be careful about what actions you take in the post-construction phase. And as I said, in all retaining structures, two important things with soil is proper compaction and proper drainage. You should have a proper drainage. Here you can see the weep holes. You should not restrain the water. Another case is this is a bridge in USA connecting Philadelphia and Delaware. It's called I-495. So this bridge has two portions, one going up and other coming down. And what they did was the Public Works Department, they brought all the building demolition waste, they call it as dirt, and dumped it on one side, the dirt. So this was a very huge one. So this triggered sorry, there was some problem. So this triggered a failure. And the columns got bent. That means I told you this bridge was two bridges actually. This right one started to tilt the other way. So there was a difference of almost more than a meter, right, between the two bridges. So the government decided they can't have it. So they ordered that section of the bridge to be removed, demolished, and new bridge to be built. So studying about failures is forensic, and studying about good performance is also forensic. So with this, I end my talk, and thank you for your patient listening, and thank you for giving an opportunity to be with you. Thank you.
That was a very informative session. Dear participants, you can now interact with Shivashankar sir. You can raise your questions and doubts. Dear participants, you may raise your questions, or you can scribble down in the chat box.
Okay. There are no questions.
Since there are no questions, okay, Hanman Jadhav sir has responded as, thank you sir, no questions. Since there are no questions, we shall wind up this session. Shivashankar sir,
Yes.
really happy that you could join.
Thank you.
Thank you for being with us.
Sure. My pleasure.
Thank you, sir. Thanks a lot.
Thank you. See you sometime.
Participants, we shall wind up the first session. The second session is on the topic seismic caudal provisions. Will be handled by Dr. Srikala R. She's Senior Principal Scientist at CSIR SERC. The session will start at 11:30. So we shall take a break now. We shall resume at 11:30.